Hi, I am Sanjay Patel. Today we are going to learn how to change order of integration in double integrals. First of all, let's understand what is the meaning of changing the order of integration. We know the double integral of a function of two variables given over a region E, which is closed and bounded region, is denoted by this symbol. And if a function f is integrable, continuous or nice function, then this can be expressed using the two repeated or iterated integrals as we have seen. And the two integrals are this. One can write the double integral if the region E is enclosed by the four curves x equal to a, x equal to b, y is equal to the curve of phi of x, and y is equal to say psi of x. Then we can write the double integral in this form. This double integral is expressed in this form when the region E is bounded by the four curves x equal to a, x equal to b, y equal to phi of x, and y is equal to psi of x. Here, this repeated integral is evaluated first with respect to y. So it is integrated with respect to y first and then with respect to x. But sometimes it is required to integrate with respect to y, with respect to x first and then with respect to y. Means we have to change the order of this integration. Here the first it is with respect to y and then with respect to x. You know the actual meaning or more precisely if you write this as x is equal to a to b and then we write like this, y is equal to phi of x to psi of x, f dy and then dx. So this means first this function is integrated with respect to y, keeping x constant, and whatever the result we get, we substitute these limits of integration. So it becomes a function of x, and finally we integrate with respect to x and then put the limits. But sometimes we need to change this order and we want to integrate with respect to say x first instead of this y. That means we have to write the integral in the other repeated integral form, which is known to you. One can write this same as if the region can also be expressed in terms of say four curves, y is equal to c to d, and then I can write x is equal to say phi of y to x is equal to psi of y, f d dy dx. So first it is integrated with respect to with respect to x and then with respect to y. Okay. So if the function of two variables is integrable or say maybe simply continuous over the region E, where E is a closed and bounded region in R2, then this double integral can be expressed either in this form or in this form. But if sometimes it is easy to change the order and then integrate, so the problem becomes easy. Okay, let us see all this by help of examples how to change the order of integration. So first I will take one or two examples and explain how to change the order of integration, and then finally one problem how to evaluate or how the evaluation of double integration becomes easy if you change the order. So that is the use of changing the order of integration. So the first problem, change the order of integration for the double integral given by x is equal to 0 to 4, y is equal to x square by 4 to 2 root x, f of x comma y dx into dy. So this double integral is given, and from this statement you can understand that it is integrated with respect to y first and then with respect to x. So this is the order, first with respect to y and then with respect to x. And you want to change this order. So you want to integrate with respect to x first and then with respect to y. Okay. So for this, first of all, you must write down the given limits or the boundaries of the curve of the region of integration. Here, the region of integration, whatever it is, region of integration is bounded by the four curves x is equal to 0, x is equal to 4, y is equal to x square by 4 and y is equal to 2 root x. From these curves, first step is you must plot the region of integration, and for that you should have some basic knowledge of some standard curves graph. Like this is known to us, this is parabola and this is a square root function. So we know all the graphs here. These are the two lines. And when two curves are given, it is better to first say find the intersection of the two curves. Let me check about the intersection. Here, the two curves are y is equal to x square by 4 and y is equal to 2 root x. So what can I do here is, let us put the value of, let me write this as y square is equal to 4x, squaring both the sides. Now let us substitute this in this first equation. So we get y square means, or let me put this value here. So putting y equal to x square by 4 in this equation, we'll get x square by 4 whole square is equal to 4x. And simplifying this, we get x to 4 is equal to, this is 16 and 16 for the 64x. And further simplifying, taking this on this side and taking x common, I can write this as x into x cube minus 64 equal to 0. Okay. And finding the roots of this equation, we get x is equal to 0 and x equal to 4. Remember, I am not taking that quadratic factor because it has say imaginary roots. We are interested only in the real roots of this equation. So we get x equal to 0 and x equal to 4, and we substitute these points in the given equation and find the value of the y coordinate. So therefore I can say, therefore y is equal to say 0 by putting here in this equation, and by putting x equal to 4, so 16 by 4, we get y is equal to 4. So the points of intersection of the two curves, the points of intersection of the two curves, of the curves rather, are 0, 0 and 4, 4. 0, 0 and 4, 4. Okay. And we also have the two lines x equal to 0, x equal to 4. So let us draw all these things in the Cartesian plane. X equal to 0 line, x equal to 4. X equal to 0 is the y-axis, x equal to 4 is the vertical line, and these are known curves. So let me draw the region of integration using these four curves. Okay. You can also notice that when you put x equal to 0, you will get y is equal to 0 from this. When you put x equal to 4, you will get y is equal to 4. So these lines also intersects these curves. So let me draw this way. So this is y-axis, then so this is x-axis. Okay, this is origin, x-axis, and this is y-axis. First I draw the graph of root x, which will be something like this. Say it may go like this, and the graph of the function y is equal to x square by 4, which is a parabola, Okay, this is y is equal to 2 root x. Let us call this as y is equal to 2 root x. Roughly we'll get this kind of graph, and y is equal to another graph I am taking as, so y is equal to x square by 4. It's a parabola symmetric about this y-axis, and it is intersecting here, so it will go like this, the graph of parabola. This is, say, y is equal to x square by 4, and we know both of these are intersecting at the point 4 comma 4 and 0 comma 0. That we obtain the points of intersection of these two curves. So these are the points of intersection. Further, the region of integration is the area which is bounded between the four curves. One is this x is equal to 0, that is y-axis. This is y-axis equation is given by x equal to 0. Another is the line x equal to 4. X equal to 4 is the line passing through the point 4 and say perpendicular to x-axis, or you can say parallel to y-axis. We put here. Okay, so this is the line x is equal to 4. So the region of integration is the area bounded between x equal to 0, x equal to 4, y equal to 2 root x, and y is equal to x square by 4. So this is the region of integration. Okay, so this is my region E. Now we are given that the function f, which is arbitrary function in this problem, it can be any function, it is integrated with respect to y first. And now we want to change the order and we want to integrate with respect to x first. So what we do is, for integrating with respect to x first, we always take a strip parallel to x-axis in the region of integration. So I will take a strip parallel to x-axis like this in the region of integration, and one must check that both the ends of the strip lie on the same curve when you move this strip throughout this region. Means if the strip is over here, or if it is over here or here, anywhere in this region of integration or in this area of integration, both the ends should lie on the same curve throughout the region. Means throughout the region, the left end curve or left end of this strip lie on this say yellow curve, that is y equal to 2 root x, and throughout this region the right end point of the strip lies on the pink curve, that is the parabola y is equal to x square by 4. Okay, so if such a situation is there, then it means our region is nice and it is regular. Such a region I will call a regular region. If it is not regular, means for all position of the strip, the left end curve and the right end curve of the strip, this is the left end point and this is the right end point of the strip. If this do not lie on the same curve, then we have to say split the region into more parts to make it regular. So this is a regular region example. I will take another example in which you will understand what happens if the region is not regular. Okay, so fine. After this, you must find the equations. We are integrating with respect to x first. So we must find the equations of these curves as a function of y. So find out the equation of these curves, that is this parabola and this square root function graph in terms of y. Here from this equation I can express this as y square is equal to 4x, and from which I will get x is equal to y square by 4. Okay, so the equation of the that square root function as a function of y, you can write as x is equal to, let me use this, x is equal to y square by 4. This is, let me call phi of y. So this left end point or left end curve of this tree is expressed as a function of y. Whenever we are integrating with respect to x, first express both the left and right hand curves in terms of y. What about this second curve, that is the parabola? Here this equation is y is equal to x square by 4. So I can write this as x square is equal to 4y, from which I will get x is equal to plus or minus 2 root y, but I will take only plus 2 root y because in this first quadrant x is positive. Here x and y both are positive. So the equation of this right hand point curve or right hand curve of this tree is x is equal to 2 root y. X is equal to 2 root y. So we have found both the ends, that's fine. And then we find what is the minimum value of, for finding the constant limits of y, because we know when we integrate with respect to x first, the limits of x will be function of y. So this I can call as psi y. So limits of x will be function of y, but limits of y will be constants. So to find the values of these constants, what we do is we find out the say minimum value and maximum value of y in this region. What is the minimum value and maximum value of y? How to determine that? For that, you can move in the upward direction, okay, and see at which point you can enter into the region. At that point, what is the value of y, minimum value of y? So we see here, if we go in this direction, suppose someone is walking in this direction, then the first point when we enter the region is this. For at this point, the limit of, the value of y is 0, and that lies on this line. So I can say this is y equal to 0. Yes, it is known as, it is x-axis. But when you exit the region, when you move in this region, and when you exit, this is not the last point. The last point occurs at this place. So this is the last point through which you can come out of the region. At this point, what is the value of y? And that is 4. So I can draw a line passing through this point and parallel to x-axis. So that line I can take as say this line, okay, and the equation of this line is y is equal to 4, and equation of this line, this point, when we enter the region, the value of y is 0 at this, and the equation of line passing through this point is y equal to 0, that is x-axis. So the required integral means we have already obtained everything, just we have to write now the final answer. The original integral I am writing first, and then we will explain how to change the order. So the original integral was this: x is equal to 0 to 4, and y is equal to, it was x square by 4 to 2 times root x f of x comma y dx comma dy. So here it was first with respect to y and then with respect to x. This we are changing to the reverse order, that is first with respect to y and then with respect to x. Sorry. So what we should do is, the first step, you write down the double integral, okay, just a little bit like this. Okay, and the function f of x comma y, we want to integrate with respect to y first, and with respect to x first, and then with respect to y. The order will come like this: dy dx. So first with respect to x and then with respect to y. So one must write the limits of x here, which is integrated with respect to first as a function of y, and limits of y here as a function of, as a constant limits. So the inner integral gives the limits of x, and that limits of x are nothing but these curves which are given in terms of y. So this, because our x varies from this curve to this curve. So x varies from phi y to psi y. That is, x varies from y square by 4. X varies from y square by 4 to this curve, that is 2 times root y. Okay, and how does y change? Y changes, as you know, it is bounded between 0 to 4. So minimum value of y is 0 and maximum value of y is 4. So y is between 0 to 4. I can say the limits constant limits of y are 0 to 4. So this is our final answer. This is the original order, and this is the changed order. So this is original integration, and this is after changing the order of integration. After changing the order. So here it is integrated with respect to x first. So limits of x will be function of y, and then with respect to y. So final integration is with respect to y. So that limit must be constant. Here you see it is integrated with respect to y first. So limits of y are functions of x, and then lastly it is integrated with respect to x. So limits of x are always constants. Okay. Let us take one more next example, as in which the region is not a nice region or not a regular region. Change the order only. Change the order of integration. Okay, for the double integral x equal to 0 to 1 and y is equal to say 0 to x plus 1 f of x comma y, say dx comma dy. Okay, so here the limits of integration are, here the limits of integration, we can write directly like this, are x equal to 0, x equal to 1, these are the limits of x, and limits of y are functions of x, that is y is equal to 0 and y is equal to x plus 1. Remember, limits of y are functions of x or constants. Okay, so it is this. So our region of integration is the area enclosed or region bounded by these 4 curves. All the curves are very simple, all are straight lines, so we can draw the region of integration very easily. So the first step and the important step in this type of problems of changing the order is you must draw the region properly. So the figure is an important part. This is y-axis, and this is x-axis. Okay, this is the x-axis, this is y-axis, origin. X equal to 0 is the equation of y-axis. This is x equal to 0 line. X equal to 1 is, say, a vertical line. So let me choose some x equal to 1 is something like this. Suppose this is the line x is equal to 1. I mean this point is 1 comma 0. Okay, this is 0 0. Another line is y equal to 0, that is x-axis. This is y equal to 0 line, this one, and y is equal to x plus 1 is a line passing through 0 comma 1, and when you put x equal to say 1 here in this, you will get, means the intersection of this with x equal to 0. Let me put this way, this is x, this is y, and I am taking y is equal to x plus 1. So when x equal to 0, one must put the constant limits 0 and 1 and get the value of y in these curves. So x equal to 0 gives you y is equal to 1, and when x equal to 1, you will get y is equal to 2. So this is a line passing through 0, 1 and 1, 2. So where is 0, 1 and where is 1, 2? Let us find out. So 0, comma 1, say somewhere, say suppose say 1 is here, and say 2 is somewhere here. This is 1, this is 2, and now I am taking line which is passing through 0, comma 1, and yes, like this. It is intersecting. This is 2, so it must be somewhere here. If this is 2 and if this is 1, then for x equal to 1, y is equal to 2, so it should be somewhere here. Let me make it down. Okay, fine. So these two lines are intersecting at the point say 1 comma 2 and 0 comma 1. Okay, so region of integration is the area bounded between these four lines or these four curves. This is y is equal to x plus 1, this is x equal to 0, this is x equal to 1, and y equal to 0. So the region of integration is the region, is the region between this. So this is our region of integration. Okay. Now we are given the order of integration like this in the problem. It is integrated with respect to y first and then with respect to x. And we want to change the order of integration. So first we integrate with respect to x. Remember, in the region of integration, if you want to integrate with respect to x, then in the region of integration, you take a horizontal strip. So we should consider a horizontal strip in the region of integration. Suppose if I take a strip like this, okay, and in this region of integration, for all the position of this strip, you just check that both the ends lie on the same curve. If the strip is here, the left end point lies on this y-axis, right end point lies on this line, so there is no problem. If it is here, then also the left end curve is this y-axis and the right hand curve is the line x equal to 1. But if I consider the strip over here in the region, then the left hand curve is this line y equal to x plus 1 and the right hand curve is the same line x equal to 1. So the curve is changing here. So even if I take a strip, another strip here, the left hand curve lies on, left hand curve is this y equal to x plus 1 and the right hand curve is this line x equal to 1. This is the line x is equal to 1. So that means this region is not a regular region. So we have to find some critical point when this curve is changing. The left hand curve of this strip, here in this portion it is this y-axis, and then in this portion it is this line y is equal to x plus 1. Okay, so we have to divide the region in such a way that it becomes a regular and nice region. So we have to find the critical point from which we should divide the region so that we get, say, some pieces of nice regions. You check by taking all possible strips parallel to x-axis that from which point the end curve of this strip is changing. Say, and the curve, that is this left hand curve, is changing at this position from this point. So one must draw a line passing through the point, the critical point from which this curve is changing. See, this strip initially when it is here, the left hand curve is this line, but when it is here, the left hand curve is this y equal to x plus 1 line. And this is the critical point from which the curve is changing. Let me put it properly. Okay. Okay. So the curve is changing from this point, that is 0, 1. So this is the critical point. Okay. A is a critical point in this region. What is this point? It is 1, 2. Remember that. So from this critical point, we should draw a line parallel to x-axis because we are integrating with respect to x-axis. We know the equation of this line is y is equal to what? 1 because it is passing through 0, 1. Find out the equation of this line, and from this line we are dividing the region into two parts. One is E1 and other is E2. So I will call, say, one of the region as, say, E1. Let us call this region as E1 and this region as E2. The whole region of integration is this trapezium bounded by x equal to 0, x equal to 1, y is equal to 0 and y is equal to x plus 1. Now that trapezium is divided into two sub-regions, E1 and E2, where E1 is a rectangle as you can see here with this 4 vertices A, O, and let me call this as say B, and this is as C, and this as D, so that I can refer to it. So OACB is a rectangle, that is the region E1, and the triangle ACD is another region. So the double integral which is given, you can change the order in this manner. I can say the double integral or the required double integral. Let me use some. We always write like this: the double integral which is given to us, which was x is equal to 0 to 1 and y is equal to 0 to x plus 1, f of x comma y dx comma dy. Now this integral you can express as sum of two double integrals f dy dx. We are changing the order over the region E1 and double integral over the region E2 f dy dx. So we are changing the order and we have to find the limits here for the region E1 and region E2. So whenever the region is not regular, you divide into say some sub-regions or say more pieces, so that all the sub-regions or each piece is a regular region, in the sense that now if you take any strip parallel to say x-axis in this region, then in this rectangle the left hand curve and the right hand curve is say same, okay, throughout this region of integration. And here also in the region E2, if you take any strip parallel to say this x-axis, then left hand curve is this line y equal to x plus 1, which is the pink line, and the right hand curve is x equal to 1. So both the regions are nice or regular. And now let us write down the limits of integration for each of the region E1 in the new order, that is with respect to x first and then with respect to y. So what to do is this. First we write down the limits of x which are functions of y, but in the rectangle there is no change. Here in this rectangle x changes from 0, this is the equation of y-axis, and equation of this curve is x is equal to 1. So this is your phi y and this is your psi y. So x changes from 0 to 1. X changes from 0 to 1. Okay. And how does y change, or what is the value of y? Limits of y are constants which are integrating in the end. And limits of y you can find out by entering in this region and coming out of this region. When you enter in the region E1, the minimum value of y is on this x-axis, which is 0. Okay. And when you exit the region, you will exit through this line y equal to 1, where the maximum value of y can be obtained in this region is y equal to 1. So y varies from 0 to 1. Y is equal to 0 to 1. F dy dx. This is for E1. Plus for the second integral over the region E2, f dy dx. First we have to write the limits of y as a function of, we are integrating with respect to x first. So first we have to write limits of x as a function of y, and then the constant limits of y. So how to find the limits of x? For that we take a strip here that is shown here, this strip, and see what are the end points of this, or end curves of this strip. In this region E2, if we take an arbitrary strip, then the left hand curve is given by this pink line, and the right hand curve is given by this this purple line or this blue line. In equation of this, which is y is equal to x plus 1, I can write it as x as a function of y, x is equal to y minus 1. So this line I can write as x equal to y minus 1, that is phi of y, and when you take the right hand point, that is x equal to 1, and it is given by psi y. So x changes from y minus 1 to x equal to 1, that is phi y to psi y, and that we are writing here, x is equal to y minus 1 to 1. Okay. And how does y change? What is the value of y, which are the constants? That you can find again by moving in the upward direction. When you enter in the region E2, what is the minimum value of y? The minimum value of y you can enter here through this line y equal to 1, where the minimum value of y is 1. So lower limit of integration will be 1. And when you come out of this region, the last point is here, and at that point the maximum value of y is 2. So the upper limit of integration is nothing but y is equal to 2. Okay. You can also show that this is bounded between this thing. So I can draw a line parallel to y-axis. So the region E2 is bounded between y equal to 1 and y equal to 2, and these two lines, x equal to y minus 1 and x equal to 1. So this is our final answer. So y is equal to 1 to y is equal to 2. These are the constants, and x equal to y minus 1 to x equal to 1. Okay. X equal to y minus 1 to x is equal to 1 of the function f of x comma y dy comma dx. So first with respect to x and then with respect to y. Remember, whenever you integrate with respect to x first, the limits of x will be either a function of y or constants, but the last variable with respect to which you are integrating, this limit will be always constants. Okay, so these are the two examples which shows how to change the order of integration. This was the original order where it is integrated with respect to y first and then with respect to x, and this is the new order. Okay, so this can be evaluated by this method also. And let us take finally one application of this to solve one problem, how it is useful if we change the order of integration. So let me write the third problem. Evaluate after changing the order of integration. Evaluate the double integral x equal to 0 to 1 and y is equal to 0 to square root of 1 minus x square Let me take some difficult problem. 1 upon e raised to y plus 1 into square root of 1 minus x square minus y square. I am adding the brackets to make it more clear. Dx dy after changing the order of integration. So in this example, you will see why it is say convenient sometimes to change the order of integration. It makes the problem easy. If you try to integrate with respect to y first, both these functions are complicated. It is e raised to y plus 1, and this is square root of 1 minus x square is constant. You can take and then minus y square. It is very difficult to integrate with respect to y first by known methods of our integration. Let me first draw the region of integration, then I will change the order and then evaluate the required integral. So let us write the solution. Here, the limits of integration are x equal to 0, then x equal to 1. So they are the two lines. This is y-axis. Then y equal to 0, that is x-axis. And y is equal to square root of 1 minus x square. Remember, it is integrated with respect to y first and then with respect to x. Okay. So limits of y are always here functions of x or constants, but limits of x is always constant. That is the last variable with respect to which is integrated. Using this, we'll try to draw the region of integration. These three are simple, they are straight lines. What about this curve? What is it? If you simplify this, you will get y square is equal to 1 minus x square, and that gives you x square plus y square is equal to 1, which is nothing but a unit circle. So a region of integration is the area bounded between these three lines and the unit circle. So let me draw the figure first. So I'm taking and this is my x-axis, this is y-axis, origin. Now let us draw a circle, unit circle with radius 1 and center at 0, 0. Let's choose some let me shift this, put it here. So this is a unit circle. And let us go back and see what are our limits of integrations. X equal to 0, x equal to 1. X equal to 0 is this line. This is x equal to 0, that is y-axis. X equal to 1. X equal to 1 is the line parallel to y-axis. Let me draw that line. And passing to the point 1, 0. So this is the point, this is a unit circle. This equation is x square plus y square is equal to 1. And this is the line x is equal to 1, because this radius is 1. This point you can take as 1 comma 0. This point is say 0 comma 1. Okay, and this is 0 0. Equation of x-axis is y equal to 0. So a region of integration as it is given lying between x equal to 0, x equal to 1, these two lines, y equal to 0, and the equation y is equal to positive square root of 1 minus x square. Remember, equation of a circle is, this is something important I am explaining, x square plus y square is equal to 1, and if you write y square is equal to 1 minus x square and then take the square root, we will get y is equal to plus or minus square root of 1 minus x square. So there are two equations. The positive sign gives you the equation of the circle in the positive part of, that is positive value of y, which is above the x-axis. So this whole arc from this point to this point, it is given by y is equal to square root of 1 minus x square. So equation of this arc is y is equal to square root of 1 minus x square. But if you are considering the lower arc, if you are considering this lower arc, this one, then its equation is given by y is equal to, this equation is given by y is equal to minus square root of 1 minus x square. This arc, this lower end, if I name it, this is A, this is B, this is C, and this is D, then the arc CDA, this arc is given by y is equal to minus square root of 1 minus x square. But our region of integration is the area enclosed between this x equal to 0, x equal to 1, y equal to square root of 1 minus x square, and this x-axis. Means our region of integration is the portion of the unit circle lying in this first quadrant. So this is my region of integration. Okay. Now what I want to do is I want to change the order of integration. We are given first with respect to y, then with respect to x, because I want to evaluate this difficult integral, this complex problem, by changing the order of integration. So I will change the order, that is first with respect to x I want to integrate, and whenever you want to integrate with respect to x first, you take a strip parallel to x-axis in the region of integration. So if you take a strip parallel to x-axis like this, then let me remove this, not proper. Take a strip parallel to x-axis in the region of integration and see that both left endpoint and the right endpoint lies on the same curve for all the position of the strip in this region. If the strip is here or if it is here anywhere, the lower, that left end and the right end lies throughout this region on the same curve. The left end point, the left end of the strip lies on this line y equal to, y-axis, that is x equal to 0, and the right end point of the strip for all its position lies on this circle. So it is a regular region. So there is no problem. After deciding that region is regular, we should write down the equations of the endpoints as a function of y, x as a function of y. This is x equal to 0, we know very well, this line. But the equation of this right end point or right end curve, this right hand end point of this strip is lying on the circle, whose equation is this actually, but now I want to express it in as a function of y. So this we can write equivalently as x is equal to square root of 1 minus y square. You know, from this equation, if you make x as a subtract the formula, you will get x is equal to plus or minus square root of 1 minus y square. But for this, x is positive on this side, so our equation of the arc BA, this arc BA will be given by x is equal to square root of 1 minus y square. So this is x is equal to phi of y, and this is x is equal to psi of y are the required limits of x, which are functions of y. How to find the limits of say y as a constants, because final variable is y. So limits of y you can obtain by determining what is the minimum value and maximum value of y in this region when you enter or when you exit the region. When you enter this region, the first point you get is on this line, that is x-axis, and it is given by y equal to 0. But when you exit the region, you cannot exit through this. The last point in this region is this point. It is given by 0, 1. So we have to draw a line passing through this point and parallel to, say, this x-axis. Okay, so we can now say the region is bounded between x equal to y equal to 0 and this y is equal to 1, because this point is 0, 1. So if I take a line passing through this, it is y is equal to 1. Let me keep it this is line y is equal to 1. So these are the constant values. So y equal to 1, this is y equal to 0. So the required integral, you can write like this. Required integral, we have to integrate with respect to x first and then with respect to y. So limits of x will be a function of y. That we have understood that they are given by the end points or end curves of these strips. The end curves are x equal to 0 and x equal to square root of 1 minus y square. So I will write x equal to 0, that is the left hand curve, this x equal to 5y, and the right hand curve is this, which is given by x equal to square root of 1 minus y square. And limits of y are always constants. It is the last variable with respect to which we are integrating, and that constants we have obtained when we enter in the region. The minimum value of y is 0, and when you come out of the region, maximum value of y is, say, it is here, that is y equal to 1. So this is the new order, and we want to integrate our function. What was that function? 1 upon e raised to y plus 1, and this I must write 1 upon e raised to y plus 1 into square root of 1 minus x square minus y square, and now first with respect to x and then with respect to y. So this will be the order, dy by dy dx. So first with respect to x and then with respect to y in this order. So now let us evaluate. You will see that if I consider this order, the problem becomes very, very easy. This is equal to y equal to 0 to 1. Then when you integrate with respect to, say, x first, this y is constant. Let me write here x equal to 0 to square root of 1 minus y square, and first we are integrating with respect to x and then with respect to y. So that is the meaning here, and this is constant when you integrate with respect to x first. So I am keeping it outside of this integral sign, so it will not disturb you. 1 upon e raised to y plus 1, and the term which contains the variable x I am keeping like this, 1 minus y square minus x square. Okay, now let us integrate this, which is very, very easy. Can you realize how to find the integral of this thing? This is equal to integral 0 to 1, then 1 upon e raised to y plus 1 into now integral of this you can think as that something square minus a square minus x square, and you know the formula of integral of 1 upon square root of a square minus x square dx. What is that? It is sine inverse of x by a. So your a is this thing 1 minus y square square root. So what should I write here? I must write the integral of this as sine inverse x upon a. X is the variable, a square minus x square form. Sorry, I should write only x, not x square. Say x upon a. What is a? A is the square root of 1 minus y square. Just compare with this formula. X is x and your a square is 1 minus y square. A square is equal to 1 minus y square. So a is equal to square root of 1 minus y square. And this, let me make it seem short. So it is x upon this. And limits of integration are x equal to 0 to square root of 1 minus y square. And then whatever answer we get is to be integrated with respect to y. So integrated, this function is integrated with respect to x first, and now we are going to substitute the limits of integration. So this is equal to y equal to 0 to 1 as it is, 1 upon e raised to y plus 1 as it is, and now putting the limits, these are the limits of x, remember, this is also x equal to square root of 1 minus y square. So substitute x, these limits wherever x appears, so I will get sine inverse of putting x equal to square root of 1 minus y square, denominator is as it is, minus by the rule sine inverse of lower limit of integration, that is 0 upon square root of 1 minus y square. Okay, so what should I write here actually is not like this. I must write directly, I must write sine inverse of 1, because this becomes 1 and this becomes sine inverse 0. If you don't understand, you can write both the steps into dy. So this is equal to what is sine inverse 1? It is pi by 2. So we get 1 upon e raised to y plus 1 into pi by 2 minus 0 and then dy. So this is equal to pi by 2 times integral 0 to 1 upon e raised to y plus 1. This is a integration of function of single variable y. Now it remains to integrate only this final step. How will you integrate this? Any idea? Yes, it's very simple. Let us divide numerator as well as denominator by e raised to y. If I divide by e raised to y, I will get 1 upon e raised to y here. If I divide every term in the numerator and denominator by e raised to y, I will get 1 plus 1 upon e raised to y. Dividing this by e raised to y, it is 1. Dividing this by e raised to y, we get this into dy. So what is the effect here? We get pi by 2 times integral 0 to 1 e raised to minus y upon 1 plus e raised to minus y. Now if you observe this, you can see that this is the function fx and its derivative is there in the numerator. So this denominator, if you call it, is fx or say fy, and the numerator is f dash of y. So f dash x upon fx type of thing. But what is the derivative of 1 plus e raised to minus y? It is e raised minus e raised to minus y. Derivative 1 plus e raised to minus y is 0 minus e raised to minus y. So I need a minus sign over here. I will put minus sign, but there is no minus, so I will make it plus by putting one extra negative sign here. So multiply by minus 1 and 2 times like this. So this becomes minus pi by 2, and now by using that formula of integral of f dash x upon fx as log mod fx, what I will get is log of mod of 1 plus e raised to minus y, and this is to be evaluated from 0 to 1. Putting the values, we get our final answer. So this is equal to minus pi by 2 into putting y equal to 1, what I will get is log of 1 plus e raised to minus 1, okay, and putting y equal to 0, let me write minus sign here, fb minus fa, that fundamental theorem. So it is log of 1 plus e raised to minus y. So it is e raised to 0, okay, like this. What is e raised to 0? That is 1. So it is log 2. What I will get is finally minus pi by 2 into log of 1 plus e raised to minus 1 by 2, because this is nothing but 2. 1 plus 1 is 2. So our final answer is this thing. Okay. So as you have seen that problem of double integral becomes easy when we change the order of integration. Okay. In this it was integrated with respect to y first and then with respect to x. But we have changed the order and we have integrated with respect to x and then with respect to y and evaluated this double integral. Okay. So this way you can change the order and solve the problems of double integral in a simple way. So I think you must have understood by now. So just keep on watching this and try to understand how to change the order of integration. In the next lecture, we'll take some more interesting problems of only changing the order of integration. So till then, goodbye. Thank you.